In this session, let us look at closed loop operation of DC-DC converter. Let us take an example of a buck converter. This is a buck converter. You are familiar with this topology, but note that you can work with any converter. The principle of closed loop operation is the same. Call this Vi, L, C, or not V naught. And we would like to regulate V naught. And the control input is here in the form of duty cycle, DTS. So let's say that is the control input, D. Now let us build the control portion of the schematic. So let us have a reference, a feedback quantity, plus and minus. We are comparing it, and let us pass it through a control block. And the output of the control block will give you the control signal, which will be compared with a triangular waveform, triangular carrier, to generate pulse width modulation and steering that we have discussed. And then from the pulse width modulation, it will go to the gate drive circuit. We have discussed the gate drive circuit and protection, and then goes to drive this switch. Now this feedback here will be the output feedback. So we are sensing the output. If we are controlling output, we have to sense the output, pass it through a sense circuitry, which means it could be made up of op amps for stepping down, filtering, and then scaling. And the output of the sense circuit is given here to this compare circuit in order to do the control. So you have V naught reference and V naught feedback. So how it operates is that, now let us say V naught here increases, this will increase, here it will increase, V naught feedback increases. So if V naught feedback increases, V naught ref minus V naught feedback will decrease, so error will decrease, and the output of this will decrease. The pulse width modulation signal will change in such a direction to decrease the drive duty cycle, and therefore once the duty cycle decreases, output will decrease and come back to its original position, operating point. And this is the closed loop action for one direction, where V naught increases, starts with some V naught increase, and the V naught increase could have occur due to any disturbance in the load, in the input voltage, or even temperature. If V naught decreases, also the action will be in similar way. Here it will decrease, V naught feedback decreases, error will increase, this will increase, pulse width modulation, pulse width increases, D will increase, and then therefore V naught will increase, and it will pull it to normal operating point. So this is the control action that you will see. It is now required that we design the value of this controller gain K. So if we properly choose this controller, then we can ensure that the error here will be 0, and the V naught feedback will match V naught reference, and your output will be regulated as per the reference, desired reference. So let me introduce some variables. This is error E, and the output of the controller, will call it as a control voltage VC. This control voltage in fact will be comparing with the carrier, triangular carrier, to generate the pulse width modulated waveform. Now let us focus on this part, irrespective of all the other parts of the system. Now if we see here, the relationship is VC is nothing but E into K, error into controller gain. So let us say E error is equal to VC by K. When can we get the error as 0? There are only two possibilities. Either VC should be 0 or K should be infinite. Now if you take the case where VC is 0, which means you are grounding this portion. So if you are grounding this portion and making VC always permanently 0, then there is no closed loop. Becomes an open loop system. So it cannot be that. VC has to be allowed to vary and make K infinite. If you make K infinite, whatever may be the variations in VC, E is always 0. The error is always 0, which means that the output is regulated. The output V0 feedback and V0 reference are the same, and which means that the output here V0 is as per the desired reference V0 ref. So in order to achieve desired control, we have to make E going to 0. So if E tends to 0, which means that you have made K tending to infinity. Now this is the important rule or important control principle that you have to remember, whichever be the system. You have to make the controller gain as high as possible to achieve error tending to 0. However, there are many problems in trying to make controller gain infinite. So we need to apply some constraints, and under some operating conditions we will try to make K tending to infinity. So let us have a look at how we go about doing that. So now let us look at the controller gain K. Now I'm going to draw a graph of frequency. On the x-axis you have frequency, on the y-axis you have the gain, the magnitude or the gain of the controller, and I'm going to express as 20 log based on K in the dB scale. So now let us use this graph to understand K a bit better. The system is going to be in various states. It will be in the steady state, it will be in a transient state, and it will be transiting from transient state to the steady state. So when you say steady state, it means omega is 0. That is, it is this area here near omega 0 will be the steady state zone. And as omega is, as we are going more towards the right part of the x-axis or the omega axis, frequency is high, which means that you are in the transient zone here. So let me mark this portion. This is roughly the steady state zone, closer to the DC and therefore low frequency region. Therefore we can call this as the steady state zone or the low frequency zone. All this portion, the higher frequency region, can call the transients zone. All the dynamics, they are all occurring in this region of the omega scale. We can call this as LF, low frequency region, or this as high frequency region. I have drawn here a curve, a green curve here, and this is the noise curve. See from here that the noise is low in the low frequency region and the noise is more in the high frequency region. The systems are more sensitive to noise, the high frequency region. So therefore, if we go by this rule that K should be infinite, the controller gain should be infinite, it will amplify noise throughout all the frequencies. So if I place the K controller gain infinite here, means this is very high gain, it is going to amplify not only the signal, it is going to amplify even the noise everywhere. And the noise which is pretty significant in the high frequency region, especially the measurement noise, sensor noise, you will see that they will get also amplified to very high value, large value, and VC will be mostly noise, it will be swamped by noise, and then you will not get any meaningful control. So therefore, we cannot just put K equal to infinite throughout spanning all the frequency regions. You need to have K is equal to infinite only during steady state, let us say more closer to the DC here, and then K should become lower, smaller at higher frequency regions. So now that is the technique that we will adopt to shape the K curve as frequency changes as a function of frequency. Let us begin with the gain of infinity near DC, near the steady state part. So if there is a gain of infinity, then the error is 0. So you will get 0 steady state error. If you start from here, let me draw a gain curve K like this, which means it is going down at minus 20 dB per decade. So here it is infinite, and this type of the shape of the gain curve is given by our familiar integrator which is written as 1 by s as a transfer function. So as omega tends to 0, omega is tending towards DC, the gain K will tend to infinite value. So around this region it is infinite, the gain is very high, error is 0, almost close to 0, and you have a steady state accuracy of 100%. Now as the system moves towards higher frequency zones during different points in the operating region, you would like to have the gain K lesser and lesser as the frequency goes higher. The reason being, as I told before, the noise is larger as you start going towards high frequency, and therefore you have to reduce the gain, attenuate the gain if you want to get meaningful control signals. Now this is just plain I control. You just have 1 by s integral, and that is I control. I could have chosen, instead of this minus 20 dB per decade line, I could have chosen this line. This also is a minus 20 dB per decade line starting from another infinite value. It's a family of infinity. Or I could have chosen another minus 20 dB per decade line like this. Or I could have chosen a 20 dB per decade line above the one that I have chosen. So which one should I choose? So let us introduce one more degree of freedom. K is Ki by s. So I have put one more variable. Instead of 1 by s, I put Ki by s. Ki is equal to 1 is this thick blue line which I have chosen. For any other value of Ki, you have these parallels. Now, if I have to include Ki into this figure, the difference between this and this would be 20 log based on Ki. So I know which parallel to pick. If I start picking parallels as it starts to intersect the omega axis towards the right, the bandwidth is higher. So this is Ki is equal to 1. Now you see the points of intersection. This is the unity gain bandwidth product. So the gain bandwidth. So when you compare this parallel intersection with respect to the blue line that we have selected, you see that this parallel is having a higher gain bandwidth. The one here has a lower gain bandwidth. The one here has still lower gain bandwidth. So the speed of response is the one that is going to be affected by choosing the parallels. So let us now write down our controller. Controller has a Ki here, then pass through an integrator, and you have the control signal. This whole put together is Ki by s. Now let me draw the time graph. So this is time t, and then let me have a step what is the step response to a step in V0 ref? This is V0 ref. So what happens to the output? The output can be like this, depending upon what value of Ki. Let's say I have chosen a Ki which is corresponding to this line. So you have a very slow response. Then let us say I choose this line which is having slightly higher gain bandwidth product. So it will be slightly faster. So you see that as Ki, you choose the parallels with Ki moving, increasing. you will have faster and faster response. So here also ki increases in this fashion. So let us say the one that we have chosen, we could probably have a ki coming like this, and you could see it reaching steady state quicker. Like that, if you choose a higher one, it would probably go much quicker, and then you choose one that satisfies you on the oscilloscope. Then let me now introduce one more component, a component like this in parallel. I'll call that one as Kp, just a proportional gain, and this proportional gain is added up to the integral one also. So you add it up in this fashion. So this is error, and this is we see the control signal. Now together you will see this is Ki by S plus Kp will be the transfer function between Vc and E. So this can be written as S in the denominator, Kp into S plus Ki by Kp. So you see that there is a 0 coming into the picture. So this is an integrator, that is the integrator that continues to stay. There is a 0 at some frequency point on this x-axis Ki by Kp. Now let us say at some point I design and place this as the Ki by Kp. So at this Ki by Kp value of frequency, I place the 0. So what should happen? The pole is giving a minus 20 dB per decade, 0 will give plus 20 dB per decade. The plus 20 dB per decade and the minus 20 dB per decade here will cancel and flatten out in this fashion. So what have I achieved with this? So you see, if I had not put this Kp, the gain would have fallen down like that. But now I am gaining extra gain as frequency changes. So I am improving the high frequency gain in this fashion. The result is that in the time axis, this is the high frequency part, the transient, that is the high frequency part, transient part, this is the steady state part. So you will be pulling up the transient part because the gain has increased. You will pull up the transient part. And then after it starts going to the steady state part, you will see it is only eye control that comes into the picture. The baton is handed over to the eye control. So if you see, the whole response may look like this with a Pi. Initially the P comes into the picture. The P is actually improving the transients, and then after the transient has passed going to the steady state, the baton is handed over to the eye control, and you will see a response something like that. So this way you try to include a PI controller. How do I choose the values of Ki and Kp? The step is very simple. You don't include Kp first. You only start with Ki, and Ki very low value. Start with very low parallel. So keep on increasing Ki gradually, keeping Kp 0. Ki gradually you increase till you get to a response with pure eye control that is best. And then you stop at that value. And then Kp is only going to improve the dynamics. Steady state, Kp is not going to touch because Kp comes only at the higher frequency zone. As the low frequency comes into the picture, it is only eye control. So you have taken care of eye control. First you have to take care of the eye control and fix your steady state response. So that is these responses. So once the steady state response is fixed, then you try to pull up the dynamics by introducing Kp. So Kp also you try to increase from 0 onwards, gradually increase Kp. That keeps adding up here the improvement in the dynamics, and then it will try to pull it up, and then at some value you will see that it is best. Beyond that it will start to probably have damped responses, so don't go over to that, and then you probably may have overshoots. Don't go over to that. So you stop at the best response you think you can achieve by looking at the scope, and at that value you stop at the value of Ki and Kp, and those values of Ki and Kp you plug in and you have your PI controller. We saw that the controller K can be a PI controller, and how we can get the parameters of the PI controller Ki and Kp we just now discussed. I want to introduce one more concept called the feed-forward control, which will help the PI controller to be more robust and faster. So let me have this XY axis. On the X, I am going to have the duty cycle D. On the Y axis, it is V0. So V0 and D are related. V0 is the output of the buck converter, and that is the controlled variable. D is the input to the buck converter. It is the control input. So the relationship is D is control input. This is the controlled output. And actually, when you talk of transfer functions, it is V0 by ds in the Laplace domain. So these two have a relationship. So let me draw that. The slope is Vi. So Vi into D. So let's say, for example, D varies from 0 to 1. And let me take an operating point where this is the operating point and this x-intercept is D. I will put it as uppercase D, and the y-intercept is uppercase V0. So the relationship between V0 and D is V0 is equal to D into Vi. This slope of this transfer curve is Vi, which is fixed, constant. So V0 is D into Vi. D is actually the control input. So now let me say that due to many reasons, Vi itself can vary, so therefore the slope of this blue line can vary, or there could be a disturbance in the output, or there could be some disturbance which is reaching the output, and V0 can vary. So therefore this operating point can vary in the neighborhood of this steady state operating point that we have shown here. So let me say that D is actually not D, but D plus or minus D hat, the small indicating the small variation above the neighborhood, about the neighborhood of the operating point as D hat. And likewise on the V0 side also, on the Y axis, I will say that this is V0 plus V0 hat, where V0 hat is nothing but the variations in the neighborhood of the operating point. So in the normal PI control that we discussed till now without the feed forward control, the controller, okay, this I will just write down D is V0 by Vi, and this is coming from the model where V0 is a specification and Vi is measured from the circuit. Now why this is important is that all these variations, all the variations in control input variation D is supposed to handle the complete variation of V0. So the PI controller that we discussed till now is supposed to handle all these variations, which means that the operating point can swing between 0 to the actual operating point, and the PI controller is supposed to handle these large signal variations. As opposed to this, with feed forward control, what is it that we are going to do? We are going to use this. We said that this is the model of the system. We know that V0 is equal to dVi. We have developed this model earlier while studying the buck converter. So I know V0. V0 is coming from the specs, user specs. Vi is coming from the measurements, instant by instant measurement. So V0 by Vi is known. So this is the nominal operating point or the steady state operating point that the system should be for that given Vi, for that measured Vi and specified V0. So this information is available to me. Let me use that information which the PI controller was not using before. So you use this information and set the operating point at this. Then due to any disturbance, if there is any variation in the neighborhood of the operating point, the PI controller should only handle these small deviations. So D hat and V0 hat only the deviations about the neighborhood of the operating point that the PI controller has to handle. So these are small deviations, and therefore the PI controller is much faster to handle the small deviation. And also because of the feed forward term, this is the feed forward term which is giving guidance or direction to the controller that any major deviation, it is supposed to come and settle there. It will be more robust. So this way it is more robust and faster. So let us see how we include this feed forward term into our control. Let us now incorporate the feed forward part of the controller into this system. So I have the controller as it is existing now. Now you see that K is nothing but the PI controller, and this PI controller is handling the entire large signal swing of V0. Now I will remove that because I need to include feed forward portion also apart from PI. Let me extend that, make the connection, and here I will include the PI controller. Now this PI controller has two parameters, Ki and Kp, which we need to select just like as I told you. First make Kp 0, Ki you gradually increase from a very low value to take the parallel with low bandwidth, and keep on increasing till you get a very good response, time response, and then fix that. And after that increase Kp from 0 gradually to pull up the transient performance. So this is the error, and the output of this is connected to another summer, and that is where we attach the feed forward term, and that feed forward term is the steady state duty cycle, the uppercase duty cycle, steady state duty cycle, which will decide the nominal operating point or the steady state operating point. Now what is being fed back is V0, the nominal or the steady state V0 plus the disturbance or the variations in V0. Deviation in that V0 reference has to contain only the nominal steady state operating point V0. It doesn't contain the deviation because this is the reference. So this minus this would give you the error, which is basically the deviations about the nominal operating point, about the nominal steady state operating point. And the controller is supposed to take care of this and make this deviations 0. So you see that PI is now only handling V0 hat deviations, small deviations in the neighborhood of the operating point. And what is the output of the PI controller? The output of the PI controller is VC hat. Now VC, uppercase VC, which is a voltage which is proportional to the nominal duty cycle, is given at this point, and this VC hat is proportional to D hat, which is deviations about the nominal, because they are all proportional to time. Now on adding these two, you have VC plus, so I have VC plus VC hat, the voltage proportional to the nominal duty cycle, plus VC hat, which is the voltage proportional to the deviation in duty cycle, is together proportional to D plus D hat. So that is the voltage signal which is actually going to get modulated with this particular carrier, triangular carrier, and that PWM is driving this gate and switching on and off this buck converter transistor. So you see here the PI controller is only handling the hat terms. It is only handling the deviation terms, which is small signal terms, and the nominal steady state operating point is given from the model, because D is equal to V0 specified by Vi measured. So D is a feed forward term here. This handles the steady state part, and the deviation, any deviations, any disturbance, PI takes care, and it is handling only small signal deviations, and therefore this PI will be very robust and very fast because the deviations are small. So in this way you can introduce the feed forward term and make the controller fast and reliable.